Hello everyone and welcome to this online NPTEL course on aquatic geochemistry. In this particular module, we have been discussing the freshwater systems. For instance, we discussed rainwater chemistry and glacier meltwater compositions in our previous lecture. In this particular lecture, we are going to discuss river water chemistry. Now, when we talk about chemistry, its composition, so we first have to start, when we are thinking about anything, any system, any aquatic system, I think we have to begin with the water itself. So how does river water starts or is sourced from? So its beginning, okay, so its beginning is always with another form of water. So it is as precipitation, okay. So most likely there is rainfall or it is coming from snow melt water, and that gets slowly gets deposited in the landscape, and when it is enough to form a stream, like there is a steady supply of water, okay, when there is a steady runoff, when there is a steady supply from other sources such as groundwater, etc., then we have what we call is a small stream. If the streams grow, we get a river. Okay. So what it is in the beginning, it will evolve along its way. Okay. So it started as most likely rain. If it got infiltrated into the ground, then it's called groundwater. If all of them are emerging out as a runoff, and that runoff is it's continuous or it's for a season, then we have a seasonal stream, or we have the perennial river, which is like always flowing. That means the sources of the water is constantly coming into the system. So when we think of chemistry, it is always the entire evolution of the water as it is, the rain, snow melt, groundwater, and how it is evolving at each step, okay, along the landscape. So of course, along the landscape, gravity plays a huge important role. So the slope is always from the high slope to the higher elevation to the lower elevation. So whenever we are passing through that kind of elevation, through that zone, even if it's very the slope is very gentle slope, the water is always transporting, it is always dissolving, it is it is always interacting with whatever comes to its path. And during this kind of interactions, there is a number of other there will be a number of other parameters with which it is interacting with. Okay. There will be a freezing, there can be freezing and thawing of water and soils along its pathway if it is in the cold and higher latitudes or higher altitudes. Such such phenomena is always occurring. Then there can be spatial and temporal precipitation patterns. At certain locations you will have a lot of rainfall, at some other locations you will have very less rainfall. Temporally as well, certain times of the year rainfall is huge, other times of the year the rainfall is very low. Then there is a watershed slope, which is the dominant factor for the flow. Then there is area and type of wetlands. What kind of what kind of land is that particular stream flowing through? Is it flowing through agricultural land? Is it flowing through a forest? Is it flowing through an area which is very rocky and mountainous, or very barren, okay, lifeless? So all of this contributes to its composition. All of this controls its composition. Okay. However way it is forming, going through the landscape, it will show in its composition. How much is the soil depth for areas which does not have a very thick soil, which in fact different kinds of soil imparts different signatures. For instance, if it is very loamy soil, it will impart a different signature. If it is alluvial soil, different kind of signature. Red soil, again different kind of signature. So different kinds of soil, how much is the bedrock interacting, what kind of soil type it is, okay, what is the depth of the soil that we see surrounding the the river channel. So, all of this, how is the river interacting basically with its catchment components is how what it controls the chemistry. Okay. And there can be other types of anthropogenic modifications. There can be dams, there can be urbanization, that means there is a lot of abstraction of fresh water, that is a good water, and dumping of the used water. There can be withdrawals for agriculture, there can be withdrawals for industrial use. There can be any other kind of modification such as beaver activity, very natural, and it's hailed as one of the most transforming and engineering aspects of terrestrial ecosystems. Okay, a beaver dam can actually transfer an entire ecosystem, and this kind of example does exist. So that's why it's mentioned as an activity. Okay, so wetland conservation, a lot of kinds of activities and encroachments and everything does also impart certain stress or certain some kind of effect on the water system, and therefore influences its chemistry. Okay. So, when we are looking at streams, it may be important to look at what kind of streams you are looking at, okay, what kind of system you are working with. Okay. So, if you are working with a stream that does not join with any tributary, I mean so generally we use this method called the Horton and Strahler method. Okay. How is this method done? So, when there is a small stream, okay, with which no other stream is joining. So, that is the first order stream, that is stream order 1. Okay. When two stream order 1 they meet and they form another bigger body, then that stream is called the second order stream. Okay. So, two one order stream is mixing to form the second order stream body. If one second order stream and one first order stream is mixing, then also the subsequent stream is called the second order. So, only when the order of the streams are same do we increase the stream order. Okay. Now, if if two streams with stream order 2 they are joining, then it becomes a third order stream. So, always remember this. If this third order stream again joins with another third order stream, then only the subsequent stream will be called a fourth order stream. In case this is joining with another 2 order stream, then this will not call 4, this will be called 3. Okay. So, this is the difference. So, why do we look at this? Because every time the stream order increases, the complexity of the system increases. Every time there is we have to, the catchment area will increase. Every time we are going above the order number, we know that we are going to look at more and more complex systems. So, in the first order streams, it can be the number of sources is limited and everything, but when we are looking into a 3 order stream or when we are looking into a 4th order stream, we know it is a huge system, we know it is a very complicated system. What is river water compositions dominated by? Okay. So, the surface water chemistry, so it can be dominated by n number of things. Okay. So, in the very starting of this lecture series, we had a particular lecture where we discussed the natural sources, the geogenic sources as well as the anthropogenic sources to any aquatic system. So, the same thing applies for rivers as well, but for rivers we have seen a huge data sets, like along all over the globe we have data for most of the rivers. And we see that they can be grouped into 3 major factors. The first factor is rainfall, okay. The second is rock weathering, and the third is evaporation and crystallization. Okay. So, most of the global rivers, the large order streams, okay, the more of the bigger rivers, they have their compositions controlled by these three contributors. Again, rainfall, that means just not rain itself. Of course, rain is there, but rain also brings in a lot of other, runoff carries a lot of sediments, so all the sediments will get in, and although the composition gets diluted, okay, after a few rainfall events. So, those are the streams or rivers which have very low, dissolved the low TDS, it will have low pollutants, low everything, okay, because it is mostly a very diluted water. The second type of is the rock weathering type, okay. So, weathering dominated systems, and this is the majority of the streams, okay. So, majority of the stream composition is controlled by weathering, okay. So, that is again divided into two types, that is calcium weathering, carbonate rock weathering, okay. So, carbonate and silicate. So, either silicate weathering is dominating it or carbonate weathering is dominating it. Now, during our previous lecture in glaciers, I showed you the weathering reactions that was related to carbonate rock weathering and silicate rock weathering. So, the same types of weathering reactions are going to be active even in river water as well. Okay. So, the same reactions is applicable in aquatic systems. Okay. So, silicate weathering, we are seeing more and more silicate minerals, plagioclase feldspar, all types of quartz, silica dominated systems. So, all silica dominated minerals, they are going to react with water, carbonic acid, and they are going to form another mineral, a secondary mineral, and most of the time it is some form of clay. Again, there are variety types of clays depending on what is the source primary mineral, and therefore, you have n number of variations of silicatic reactions. Carbonate reactions are, as comparison to silicate minerals, are very straightforward, because we either have calcium carbonate or we have dolomite. So, basically we have calcite and dolomite and sometime limestones. So, these are the primary minerals which is going to dissolve. So, you will have calcium, magnesium and carbonates. So, carbonates in the form of bicarbonates will be mostly present in the freshwater systems, right. So, this is the kind of reaction that is going to dominate the system. If the stream is flowing through a catchment that has carbonate rocks, the carbonate rocks is going to dominate the weathering reactions, okay, because simply because it is much more soluble. It is calcium, magnesium, bicarbonate, strontium, all these elements which is linked with calcium carbonate systems, and of course, impurities such as uranium and few other metals, they will be high in this kind of systems. Okay. If not, if it is more of the silicate types, okay, if there is a lot of heavy minerals, if there is a lot of biotite, garnet, it is a lot of hornblende, micas, every type of minerals is mixing, and we will find all the metals in high compositions. Okay. All the metals will be in significant high concentrations. So, carbonates, they have very different kind of composition, where few elements will be very high. So, calcium, magnesium, strontium, these will be very high as compared to all the other elements, right. But for silicate weathering dominant systems, the other mineral types, okay, will also be very high. So, of course, silica will be high, rubidium will be high, strontium will be high, lithium will be high, okay. But certain transition metals groups, so chromium, nickel, vanadium, all these that are related to heavy minerals, okay, aluminum, all these metals will also be similarly high in their composition in these kind of rivers, okay, along with the base minerals, the base metals, that is calcium, magnesium, sodium and potassium. So, this is going to be commonly high in silicates, okay. Any kind of silicate, it will always be high with calcium, magnesium, sodium and potassium. Along with this, you will have a mixture of elements. Now, this is a graph showing the chemical mobility, that is mobility of the elements during the erosion and transport, okay. So, this is controlled by how mobile it is in the system, how mobile that particular element is during its erosion and transport. And how is this determined? So, it is the composition of that particular element in the water, its concentration in water, divided by its concentration in the crust. Okay. So, its concentration in the upper continental crust and its composition in the water that we have found, okay. And here is an plot of all the elements, and you will note that this is this is in comparison with sodium. So, here we have sodium equal to 1. All the elemental compositions has been normalized with respect to sodium. That means, whenever we think about an element, whether it is more mobile than sodium, because sodium is one of the most reactive, most soluble, most mobile elements. So, therefore, we are going to have sodium as our normalizing agent. So, you have sodium here, and with respect to sodium, which elements are more mobile, and then there are which elements are almost similar or less mobile. Okay. These are the less mobile elements. And you can see here, more mobile than sodium is magnesium, and molybdenum, antimony, arsenic, selenium, boron, cadmium, radium, sulfur, palladium, carbon, chloride. So, chloride is it's like way more mobile as compared to sodium. It is more than 100 times more mobile than sodium, okay. And similarly, these elements, certain other elements, they are more reactive, they are more volatile in nature, they are more mobile in nature, okay. Calcium, strontium, uranium, again extremely mobile in nature, whereas titanium, zircon, aluminum, tantalum, hafnium, these are all elements which are far less, almost close to 1,000 times less mobile as compared to sodium. That means, even during the reactions, they will not like to go the fluid, they will remain with the minerals, okay. Therefore, their decomposition and requires complete breakdown, complete shattering of the primary mineral phase, okay. These are very minerals and elements that are found in very less concentration in the water. And in this other chart, we have what we call the global elemental average composition here, okay. And this average, the data has been combined for many hundreds of rivers all around the globe, okay. So, here you have the total suspended world flux, okay, and how much it is there. So, aluminum, how much aluminum is there in the suspended sediments, and how much is it there in the dissolved phase, okay. So, this is the dissolved phase concentration, that is microgram per liter, and that is the dissolved world flux, okay. So, when you have flux, it is the river flux, average river water flux multiplied by the concentration. So, the number is huge. So, as you can see, it is some 1200,000 tons per year that is going from the rivers to the final sink, that is the ocean. Okay. And this is a chart which has been limited to, you know, limited to rubidium. Okay, when I was cutting and copying this chart, but this is a bigger chart and you can find this in Weers et al. 2009 in Science of the Total Environment article. Okay. So, as we were discussing, the composition of river water is dominated. Now, this we can easily make a plot when we make a plot of TDS versus a cationic ratio. So, this can be, you know, sodium divided by sodium plus calcium, and as you can see here, you see this kind of plot where certain, you know, this, just forget about the dotted lines, the dotted line just shows how the data plots. Okay. But when the data plots, we see that certain, you know, certain water systems, they have this very high ratio as well as very high TDS, and this data is mainly from the oceans. Okay. Then rivers mostly lie in this zone. Okay. Majority of the rivers or the large rivers lie in this zone, while majority of the smaller rivers lie in this zone. So, we have what we call this kind of series where there is sea water at one end, this is the zone of rock dominance, and this is the zone of precipitation dominance. So, we have evaporation precipitation playing role here. So, it is chemically weathered you know, composition that through evaporation and precipitation is moving through higher TDS. For instance, Caspian Sea, Baltic Seas, they are here. That means a lot of evaporation, evapotranspiration enrichment has happened, which makes these, you know, enclosed water bodies so very high you know, dissolved load content. Okay. And they are so salty, the sodium concentrations are so high. So, this is just simply you know, like oceanic water. So, it is very you know, that is the kind of composition that we see. And again, if it is small rivers, small streams, then we see that mostly it is here, that means the TDS is very low, but the sodium and composition can see you know, be high. That is because it is coming from the atmospheric, because yesterday, you know, in our last lecture we discussed that, you know, whenever there is rainfall, the rainfall will have high sodium because the moisture source itself is the ocean. The moisture source itself is the ocean. When ocean is the source, the sodium will definitely come from the ocean source. So, this is the kind of, this is called the Gibbs plots, and it is a very, you know, fundamental plot that we make when we have, and when we try to understand that what kind of rock you know, dominance it is having. Okay. The other kind of plots that we often see is these kind of Piper diagrams, and this particular data has been plotted from the Canadian Arctic archipelago rivers. These Arctic rivers, and this is the journal and the author name which you can find, you can later refer to. So, these kinds of Piper plots help us understand what kind of weathering was dominating. Okay. So, in this bottom left hand triangle, we have sodium and potassium, we have calcium and we have magnesium. In the right hand triangle, we have sulfate, we have chlorine and we have bicarbonate. And in the middle, we have this you know, diamond shaped, we have calcium, magnesium, we have bicarbonate here, we have sodium, potassium and we have sulfate and chlorine. Okay. So, this kind of plot, okay, we not only plot, we are also going to plot some other end members. For instance, we are going to plot seawater or precipitation that is having, and what does the line show? The line shows a composition, right. This is 20% of this is bicarbonate, the rest is something else. Okay. So, this line shows 20% bicarbonate, 80% chloride. Okay. So, this is that particular line. Okay. So, this black boxes are the end members okay, and members of different types of weathering. So, we have seawater and precipitation here, we have seawater and precipitation here, we have seawater and precipitation here. Then what we have sulfate salt dissolution, SSD. That means there is some kind of sulfate salt that is dissolving in the catchment, and we have here we have sulfate salt dissolution, SSD. Okay. Then what we have sulfuric acid silicate weathering. So, generally when we have silicate weathering and carbonic carbonate rock weathering, we are going to form mostly some kind of acids, right. If the bicarbonate, if the carbon dioxide is dissolving in water, we form carbonic acid, and that carbonic acid is interacting with the silicate rocks, and we say it is carbonic acid silicate weathering. If that carbonic acid is again weathering the carbonate rocks, it is carbonic acid carbonate weathering. Okay. So, for that we have this kind of composition, okay, CaCW kind of composition. Okay. Now, if there is interaction with the sulfate or the sulfur dioxide that is there, then we can also form sometimes sulfuric acid. Okay. And that sulfuric acid, if it reacts with the system, then we have sulfuric acid silicate weathering or sulfuric acid carbonate weathering. So, here is a sulfuric acid carbonate weathering, okay, kind of composition. Again, here we have the sulfuric acid carbonate weathering kind of interaction. Here we have the sulfuric acid carbonate weathering or carbonic acid calcium carbonate weathering. So, this is carbonic acid carbonate weathering. So, this kind of compositions helps us understand okay, what kind, and we are going to compare this with our data and see okay, which type of compositions is it lying. If it is something like this, okay, that means we know that this is a mixed signal, right. There is a mixed signal. So, there is some kind of mixing happening and we get a mixed signal here, right. We are seeing both calcium carbonate weathered and silicate weathered, and therefore, we see such kind of plot. So, such kind of interpretation is very useful when we are going to see when we are having a data and for the first time we plot the data. So, it is useful when we plot the data, and it is not only this, we can have multiple other plots. For instance, we showed the ratio plots. For instance, we can have calcium by sodium versus magnesium by sodium, and we have different rock types and how if the water interacts with that kind of rock type, that kind. So, we can have sometimes this is carbonate and this is granite or basalt, and this can be evaporite, and we can see some other rock end members and see okay, where is our data falling. So, we can have molar ratio plots, we can have different kinds of, we can have silica by sodium, we can have calcium by sodium, we can plot with calcium by sodium and strontium by sodium. Okay. So, such elemental molar ratio plots again are extremely useful when we are trying to understand what kind of weathering is our rock types is our river water composition dominated from. Now, when we talk about river water, okay, its chemistry is not very simple. It's a very well mixed system. It has multiple processes happening simultaneously, continuously. Okay. So, it is a very complex open system. Okay. For instance, let's break down the components one by one. Let's break down some of the more important processes. Okay. Let's see the inputs as they are. So, first thing is the input, which is can be natural inputs. So, there is weathering, which is absolutely natural phenomena. There is rainfall, which is again very naturally it is getting added into the system. Of course, the rain can mix with a lot of anthropogenic emissions and therefore have certain composition, of different composition, but otherwise it's a natural phenomena. Nobody is causing, no human is causing and manipulating the rainfall, at least as of yet. Then there is anthropogenic, which is of the more direct inputs. The direct inputs can be agricultural, there can be industrial, there can be municipal. Also the groundwater is a natural contribution. Groundwater coming in and adding into the river water is natural, but there can also be groundwater that is coming through indirectly, because the groundwater is extracted, is used, say maybe for municipal purposes, and then that is coming into the system. Because most of the municipal water supply is, if it is not very close to a direct river source, a significant proportion of even places close to rivers, they also depend on groundwater as their major source of water. So the major source of fresh water globally is groundwater. So that groundwater, even after a lot of usage, can come to the river. Now let us look into the processes that is happening. Now processes again will be divided between inorganic processes and organic processes. Let us see what are the inorganic processes. So the first inorganic process will be the progressive weathering. When a river is coming, when a river is coming, say suppose that was point A and you are standing here and looking at this picture at point B. Now from point A to point B, there is a distance, there is a flow, there is a mixing, there is a rolling of the water with the sediments and everything. So this is continuous weathering that is happening. So a lot of progressive continuous weathering is happening. And if this is a very, if this is a system which is a mature system, then orthogenesis, clay orthogenesis can also be happening. Clay orthogenesis is also called reverse weathering. That means the minerals that is dissolved, they may start precipitating out. The clays can start the minerals dissolve, they can start forming clays and they can start precipitating out. So clay orthogenesis happens when the river is at a mature stage. You will not see it in the young stage of the river. Then apart from these interim sediment interactions, there can be other kind of processes, and those are mostly related to the prevalent physiochemical conditions such as pH, such as the redox, such as the dissolved oxygen composition. So those kind of interactions will mobilize the metals. They will control the metal concentration in the river. So pH changes, redox changes. Such kind of interactions will change definitely the metal concentration in the river. Then metal exchange reactions, that depends on the ionic strength, that depends on the salinity strength, that depends on the sediment composition. How these bottom sediments, if they are very rich in a particular metal, they can just slowly release that. So legacy sediments, they can leach those composition. Otherwise salinity, that controls the adsorption desorption reactions. That controls the complex formation reactions. So these will be controlled. So ligands, all the organics, they control the ligand formation. In our previous chapter with respect to organic matter, we have been discussing about the dissolved organic matter and how that controls adsorption and degradation and formation of chelation, ligands, which ligands can form metal complexes that allows more favorable more soluble, more mobile complexes that allows the metals, rather than settling down, to remain in the stream itself. So they are going to remain in the water column, they are not going to settle down, they are not going to precipitate out. Again there is uptake and release by biota. So there are aquatic plants, there are aquatic animals, they are continuously exchanging all the micronutrients. So, there is iron, zinc, copper, whatever mineral is there which is like a nutrient which is required for the for the metabolic activities, they are going to be exchanged. They are going to be exchanged within the system, and of course, they will produce ligand which will favor the availability of those elements. That means these plants, these microorganisms, they release a kind of substance that kinds of binds these metals. So, this is just like finding some kind of complex molecules that binds to the nutrient, a micronutrient, say iron or nickel or copper, and makes it available for that organism. So, it is easily uptaken by that organism and it gets into the metabolic system. Then biofilms, microbial mats, sedimentation, they can help it settle down. They can trap the metals and they can just settle it down, they can remove the metals from the column. So, all these processes are happening simultaneously together, and when we see a composition, we are just seeing a literally a speck of whatever is happening, in a time speck whatever is happening, and with that speck we have to deal with all these processes. So, yes, it is a very complex system, and understanding this is very difficult if you are working with very limited data. So, what we try to do is we try to have multiple data that can lead us to multiple multiple processes. Okay, for instance, I need DOM data, DOC data to have a hold to say what kind of organic processes is happening. I need to know the physiochemical conditions, I need to see the entire metal, all the metals I need to know. I need to know the sediment concentration, I need to see what is the velocity, okay. I need to see how much is runoff coming, I need to see how much rainfall is coming. All kinds of data will therefore help me to understand why my river composition looks like the way it does. Okay. So, with this I will come an end to this lecture, and we are going to continue discussing more about river water chemistry in our next lecture. Thank you.